Hey guys, how's it going? Today I wanted to show you how to find the area under the curve of a function using Riemann integration. So let's write that out. Area under the curve. Let's also assume that our function is continuous and on the real numbers. Okay, great. So let's start by drawing a graph. Oftentimes the visual intuition helps us formalize our algebra. Sorry, I can't draw a line. Okay, great, let's do it. So let's say we have a function that looks maybe something like this. Perfect. Okay, well, if you're unfamiliar with Riemann integration, so if we want to find the area of all of this, we can do so by partitioning that area into small rectangles, right? And the more we partition this, the thinner our rectangles are, the more accurate the area will be. So that's the method we'll be showcasing today. But I'm going to attempt to do it in a way that does not use confusing notation and a way that is intuitive and makes sense, because I think a lot of people, including myself in the past, have been confused by how everything is written out. So that's my goal for this video, to show you how this is done in the least confusing way possible. Let's do it. Let's start calculating the area at x. Okay, so we're building a rectangle, all right? Maybe I want my rectangle to end here. We'll call this x plus epsilon, where epsilon is just some tiny distance from x. It's as if we nudged x epsilon units in this direction. So let's finish drawing our rectangle. Here's the end point in green. Perfect. So again, this distance here is just epsilon. Cool. So for example, if x was the number 3 and x plus epsilon was 4, then epsilon would be 1, because 4 minus 3 is 1. That's how we calculate this distance, right? We take the end point and we subtract the start point. So the length of this space will always be epsilon. Does that make sense? Okay. If we evaluate the function at x plus epsilon, then the output here, the output must be f of x plus epsilon. Great. For the sake of convenience, the next rectangle I draw, I want it to have a base of the same length as my first rectangle. So if I push x plus epsilon units away again, I'm going to land at x plus 2 epsilon. Perfect. Let's finish drawing this rectangle. So this base here would also be epsilon. Now, if we continue this process until we reach the last rectangle, then we will end up at x plus n epsilon, where n represents the number of rectangles we have. To make this drawing look nicer, let's also put the second to last point, which is x plus n minus 1 epsilon, because that's the point right before x plus n epsilon. Let's also draw some dots here. And then let's draw a point and finish closing off the rectangle. Perfect. All right, so again, this output here is going to be f of x plus 2 epsilon. And this output up here is going to be f of x plus n epsilon. Great. All right, now if we were to take the sum of all of these rectangles, then we would have the base times the height, right, added together for all of these rectangles. So we know that the formula for the area of a rectangle is base times height, In this case, our base is epsilon, so that's our base, times the height of our first rectangle. That's just f of x plus epsilon. That's the output. It's a single number. That's the height of our first rectangle. Let's add the height of the second rectangle. Sorry, add the area of the second rectangle. That's epsilon times f of x plus 2 epsilon, because the height of the second one is f of x plus 2 epsilon. If we continue this, we're going to add up until epsilon times f of x plus n epsilon. Remember how we said that as epsilon grows smaller and smaller, the area will become more accurate? Let's capture that idea here by saying the limit as epsilon approaches 0. So this is saying, hey, let epsilon, continuously get closer to 0. That's going to partition our rectangles, our area, into finer and finer little chunks, right? So imagine epsilon is really small, then maybe our rectangles are this size. And if we add these all up, if we continue this in both ways and add them up, our area will become more and more accurate. Because right now, if epsilon's large, this is our margin of error. Look at all this extra area that we're adding, and it's not going to give us an accurate representation of this area down here that we want, because we're going to have all this extra red. But as epsilon grows smaller, this red error is going to become less and less. So that's why we're letting epsilon get infinitely close to 0. Say, all this written out, it's just a lot to write, and I don't want to write that every time. Let's condense this into a single summation. So this is equivalent to, we'll keep our limit here, the limit as epsilon approaches 0, of the summation from k equals 1 to n of epsilon times f of x plus k epsilon. So k is our counter. When k reaches n, that's going to be our last rectangle here. Epsilon times f of x plus n epsilon. So this entire expression at the top is equivalent to what I wrote here. Keep in mind that this is representing the area under the curve here. Great, so we have our definition of area under the curve written out. Why don't we actually apply it? Let's pick an example problem. So we'll say let f of x be equal to x plus 1. Let's find the area under the curve from x equals 1 to x equals 6. I made these two numbers up. I could have chosen any two numbers, right? As long as they're in the domain of the function. All right, let's do this. Let's apply our definition. So we defined area as the limit as epsilon approaches 0 of the summation of k equals 1 from k equals 1 to n of epsilon times. Now here's the thing. We said in our generalized formula that the height is f of x plus k epsilon. But if our f of x is x plus 1, then it must follow that f of x plus k epsilon is equal to x plus k epsilon plus 1. All I did was I replaced x with x plus k epsilon, because that's how we defined our area. So I'm going to write here x plus k epsilon plus 1, because that is what our f of x plus k epsilon is equal to. I'm also going to move this epsilon outside of the summation to make things easier to read, because that's just a constant. So I'll write this out. I'll even wrap parentheses here to show that we're summing, we're taking the summation of all of these terms added together. Now, hopefully you remember that taking the summation of all of these terms added together is the same as if we took the summation of each term separately and added that together. So we can actually rewrite this. But here's one thing I wanted to point out. Since we're finding the area under the curve from x equals 1 to x equals 6, we're starting at x equals 1, right? So I'm going to replace x with 1, because that's where we're starting. So we can just write x as 1. Okay, very good. Let's also combine like terms. So we can actually rewrite this as 2 plus k epsilon. 2 plus k epsilon. Perfect. All right, so this becomes the limit as epsilon approaches 0 of epsilon times the summation of 2, starting at k equals 1 to n, plus, and actually we'll add brackets here, the summation of k times epsilon from k equals 1 to n. All right, let's do this. So since 2 is just a constant, we can just move it over here, and I'll have 1 left, because I just factored out a 2, right? Well, let's think about this. What is this summation saying? It's saying, hey, I want you to add 1 to itself once, and I want you to do it again, and I want you to do it again until you've done it n times. Therefore, I have n ones, and this is just equal to n. So the summation of 1 from k equals 1 to n is just n. So this first one we wrote here, that's when k was equal to 1. The second one here is when k equals 2, so on and so forth until we reach our last k. So this just tells us how many times to add 1 to itself. That's n times. So we know that this first bit here evaluates to 2 times n, because this entire summation here became n, right? Okay, now this is where it gets interesting. Let's expand this part. Well, we know that this is equal to epsilon plus 2 epsilon plus 3 epsilon plus n epsilon, right? So how do we evaluate this? Well, you might be saying, hey, since epsilon is approaching 0, then maybe all of these terms will get infinitely close to 0 and cancel out, so to speak, so we don't really have to worry about it. Well, to that I say, recall that as epsilon grows smaller and smaller, our n must grow larger and larger, because n is equal to the number of rectangles we have. If I decrease the base of each rectangle, I must have a greater quantity of rectangles to account for the fact that each rectangle is shrinking. I need more to take up the same amount of space. So we basically have, it's almost like two infinities competing against each other. Epsilon is growing infinitely close to 0, and n is growing infinitely large. So these actually do not become 0. We're going to have to do better than that, right? Well, maybe we can manipulate this a little to guide our how we're going to solve this. Let's actually factor out an epsilon here and see what happens. So this becomes epsilon times 1 plus 2 plus 3 plus ... n. So hopefully you remember that the sum of the first natural numbers, the first n natural numbers, right, starting from 1 and ending at n, is just equal to n times n plus 1 over n. And I believe this was discovered by a man named Gauss a long time ago. Epsilon limit as epsilon approaches 0. Perfect. All right, I think it's time to distribute our epsilon. Let's do it. So we end up with 2 n epsilon plus, we'll say, I'm not going to square the epsilon for now, and you'll see why in a moment. So now it's like, hey, how do we evaluate this? Well, let's look at our picture again for a second. In our problem, we're calculating the area under the curve from x equals 1 to 6. So if we're starting at x equals 1, then this expression here must be equal to 1 plus n epsilon, because we said x is 1. We also know that it must equal 6, therefore n epsilon must be 5. And again, that just represents this distance right here. It's 5, right? That's my total distance from start to finish. It's n epsilon. Okay, great. So we have a value for n epsilon. So we know that this becomes limit as epsilon approaches 0 of 2 times 5 plus, oh look, I have another n epsilon right here. So this is 5 epsilon. We'll say 5 epsilon times n plus 1 over n, running out of space here. If I distribute this 5, we're going to have limit as epsilon approaches 0 of 10 plus 5 n epsilon plus 5 epsilon over n. So look, I have another n epsilon. So this actually becomes 25, because n epsilon is 5, and 5 times 5 is 25. Oh wait, I just realized I made a typo. It's not over n, it's over 2. Sorry about that. So this should be a 2 down here. I knew something was fishy. All right, running out of room. I'll be right back. All right, I'm back. So we left off at this point. Actually, that should be 2. Okay, nice. This is where we left off. So let's simplify some things. And let's actually take our limit. So we know that since epsilon is getting closer and closer to 0, then 5 halves times a number very close to 0 is basically 0. So this actually evaluates to 0. So we can say 10 plus 12.5 plus 0. We don't need to write our limit anymore because we just took it. So this is equal to 10 plus 12.5, which is 22.5 units squared. Okay, great. So we have an answer for what the area under y equals x plus 1 looks like from x equals 1 to x equals 6. But let's check our answer. Why don't we sketch a graph and calculate the area using geometry? Since this is a linear function, this should be relatively easy to do. So there's the y-intercept. We're going from x equals 1, 1. Sorry, this should say, we'll put 1 right here. 1 to 6. Okay, great. So at x equals 1, the output is going to be 2. And when x equals 6, our output is 7. So we're calculating the area of this trapezoid right here. I'm going to write this a little bit better. Cool. Let's actually cut this into 2 separate shapes so we can more easily calculate the area. Okay, well, I know that the base of this rectangle is 5, and I know the height of the rectangle is 2, which means this area is 10, because 5 times 2 is 10. I know the base of this triangle is 5. I know that the height is 5 because 7 minus 2 is 5. The area of a triangle is base times height divided by 2. 5 times 5 is 25. 25 divided by 2 is 12.5. So the area of this trapezoid is 12.5 plus 10, which is 22.5 units squared, which is exactly what we got when we calculated the area using our Riemann sum. Great, it adds up. That's good news. Okay, so yeah, hopefully you found this to be helpful, and that, if it didn't make sense to you before, maybe it makes sense now. I hope that you learned something, or at least deepen your mathematical insight after watching this video. Thank you so much for watching, and have a great day.